Professor Nanda and Professor Anirban for the invitation. Very happy to see this campus for the first time. So although the title is Multi-Armed Bandits, this is not about politics. We're not going to talk politics today. This is a technical term. I'll tell you. So first part is somewhat somewhat more basic, and then I'll talk about my own research in this the last many months. So this is something I've been working on the last 5-6 months. So I'll talk about that. So that's the picture. So the classical multi-armed bandit problem. I think the name comes from 1952. The first application of these ideas comes from clinical trials. You have multiple drugs for a particular disease, and you want to know which one works better. So it's like you have multiple arms of a bandit in a slot machine in a gambling place. You pull one arm, you get some reward. You pull another arm, you get another reward. A reasonable assumption to begin with is that these rewards from each arm, so each arm is like a probability distribution. And pulling an arm is like sampling an arm. And you want to figure out which amongst these is the one with the highest reward on average. So which drug works the best amongst all the drugs available to you for a particular disease. So that's how it started. A lot of work happened after the World War in Rand. So that's when Robbins, who was a statistician, came up with many ideas, and we'll talk about some of them as we go along. So let's just move on. So multi-armed bandit framework provides perhaps the simplest setting for sequential learning and decision making. So it's now very hot, this area in learning theory, in machine learning. Because sequential information is revealed to you and you learn a little bit. Information is revealed to you and you learn a little bit. So how to do it efficiently and in the simplest possible setting. So that's where multi-armed bandit fits in very nicely. Where is my thing here? All right, so it crisply demonstrates explore versus exploit trade-off. So let's go back to the medical example. You have a number of treatments. Now you could just take each one treatment, try it on maybe 100 people, another treatment, try it on 100 people, every treatment 100 people, see which one's working well, and then you have a very good idea of what to do. But then the drawback of that is you're using a bad treatment to treat people potentially for a very serious disease. So you want to explore which one is better, but you also want to exploit something which is doing very well, a drug which is working very well. So it captures this explore and exploit trade-off. You can also imagine kind of this generally coming up in many optimization settings, where you're exploring the space to see all the options available to you, but you also want to exploit the good options as and when they become available. So many applications of this general explore versus exploit trade-off. So I'll focus on the stochastic multi-armed bandit problem. Stochastic means that I'll assume that whenever I pull an arm, there's an underlying probability distribution from which I see a sample. As opposed to maybe adversarial setting where I pull some arms and the nature gives me the worst possible output from the arm. There's a lot of literature on that too, but I won't talk about that. I'll assume it's a stochastic framework. Specifically, we'll consider regret minimization. So every time you pull a wrong arm, you suffer some regret. You should have done this, but you've done that. So how do you control the regret? What kind of regret are we looking at? So we'll talk about this. How many of you are familiar with this at all? Multi-armed bandits. How about this to students? You've heard some of it. Okay. Feel free to kind of make it interactive. I'll have a better sense of where everybody is. And then I'll talk, so I'll focus on the things that I've been working on. These are kind of motivated from Monte Carlo methods, which is also a topic here, where pure exploration makes much more sense. So rather than explore and exploit, now you're purely exploring. And we'll discuss this in a general framework, and we'll introduce a general framework in this setting. And I also gave a cute application that I've been working on to perfect interview and perfect exam. And the way to think about it is as follows, that you go for a job interview and take our point of view, we're interviewing you. How hard should a question be when I ask you? So I'm going to sequentially decide how hard should a question be to you. I want to gauge your level, right? So with the fewest possible questions, I want to determine what your level. Are you above a threshold or not? Are you in this band? Are you an A grade student or a B grade student or a C grade student? So how can I do this very quickly, adaptively, learning from your answers, controlling the probability of making a wrong decision to a specified delta. So you give me a delta, I'm okay to live with an error of 1%. So given that I'm happy to live with an error of 1%, how should I ask these questions? And in the quickest time, decide what your grade is. So that's an application of sequential learning, so I'll talk about that as well. All this is something which I've just been working on last many months. Okay, so multi-arm bandit problem, the broad framework. So you're given k arms. So k is going to be fixed here. When pulled, give a random reward. The reward vector at time t, so this is a reward vector, xt, x1t from reward from arm 1, arm 2, arm k. Is this clear? Each arm will have a reward, yeah?
So, negative reward will be considered as your regret?
Sure. No. The regret will be that you didn't pick the best arm. When you got less than the best reward, that's your regret.
Okay.
Difference between that, yeah. So I'll talk about that, yeah. So each arm has a mean mu of I, which we'll assume to be constant. At each iteration t equal 1 to 3, learner or an algorithm is going to pull some arm, it, and receive a reward xitt. So it will receive the reward from the arm that was pulled. It will not learn anything about other rewards that were not pulled. See, you apply one treatment to a person who has cancer, you see whether the treatment is effective or not. You don't learn about what would have happened if you had applied other treatments. This is, by the way, different from the world of finance, where you're taking advice from people and investing. So I take your advice and I get to see what result was, whether I made money or lost money. But I can also see what would have happened if I had taken other people's advice, which I did not take, who had also given. That's called expert system literature, where you get feedback from a lot of experts. So that has its own kind of mathematics that goes with it. It's quite elegant. But this is the bandit setup. You see what you pull. Rewards are assumed to be independent samples from distributions, F1 through Fk. Right? These are for each arm, the samples are going to be IID, independent, identically distributed. Sorry, let me just see. Yeah. The aim of regret minimization is to sequentially pull arms so as to minimize the expected regret. So mu star is the expected reward you get from the best arm, the arm with the highest mean, which you don't know. So if you knew that arm, you would have gotten in expectation a reward of n times mu star after n pulls. But you don't know it. What you did was you pulled some arm it at step t, t equal to 1 to n, and this is the reward you got. So this is your regret. And that's a regret you want to control, right? How do you best explore and exploit to control this regret? This is kind of, in the online world, this kind of stuff is becoming more and more important because you have to learn sequentially. Information becomes available to you, and then you act upon it. So other popular objective, which I'll focus more on later, after the first 1 hour or so, is to sample till a random stopping time tau. This is called pure exploration. This is, I just carry on, and what's my regret after every step n? Here I'm going to stop after random stopping time tau, and then announce which arm is best while keeping the probability of error to a specified delta. This is what's called in computer science literature as delta pack algorithms, probably approximately correct algorithms. And this is the way to think about why would this come up, I'll explain later. But think of a Monte Carlo model that you have. Somebody comes to you, an engineer comes to you with 20 different configurations for how, say, a road network should be designed, right? Different ways of connecting roads, etc. It's very difficult for any configuration. You may have a model for how the traffic is going to come, how the traffic is going to interact, but there's no closed form solution as to what the expected congestion is going to be. So your objective could be to find amongst these 20 networks which one has the least congestion. It's a very reasonable thing to do. Engineers would do that. They have these massive models of transportation of vehicles exactly doing these things. So then the question for them is to find out which one has the least congestion. They're going to do Monte Carlo simulation. Computation is very expensive to simulate each and every network. So you simulate a network, and out comes what was the congestion in that simulation. That's like pulling an arm. So one random draw of pulling an arm. You do another network, you get another arm. You want to figure out which arm has the least expected congestion You want to do it as quickly as possible. You don't want to spend infinite amount of computational effort while controlling the probability of making a mistake to delta. So you have guarantee that if you were to make a mistake, how bad did you do? Right? So that's a very kind of a canonical example of where this kind of pure exploration comes up. So this is where you just want to explore these 20 arms and find out which is the best. You're not exploiting as you go along, as opposed to in the cancer setting, where you want to also kind of, hopefully use the best treatment you know so far for most of the patients. There you want to exploit what you know. So that's the two different gist of problems that I'm going to be focusing on. All right, aim is to achieve these guarantees in minimum expected time for these delta pack algorithms. So all right, so now, some applications of regret minimization. So why do we study this? So which drug is most effective against a disease, as I discussed, and you want to explore as well as exploit. Recommendation system. Which type of recommendation suits a particular type of customer? So you see these nowadays a lot when you go on the website. Particular kind of advertisements come to you, particular type of movies are suggested to you, particular type of books are given to you, things to buy. These are recommendations made to you. So they're trying to see, okay, amongst these 20 different ways of classes of things we can recommend to you, which one suits you the best. So they are using multi-armed bandit methods basically. Internet advertisement. What advertisement to place when a customer searches the web? So when you go on Google and you search for something, an advertisement will come up. Internet quickly figures out that we are not the kind of people who spend too much, so we don't get that many ads. But if you were to be that type, you'll get a lot more ads coming up. So that's again solving a bandit problem. In transportation, which route to take amongst many? So you're going to maybe Calcutta every day, and maybe there are 5 different routes. So you kind of explore and exploit. You want to keep on exploring, so maybe if something new is going on, you should see that. At the same time, you want to choose typically the best route that you think gets you there fastest. All right, so pure exploration, best arm problems. Now let me just talk about the other problem, which I'll focus on later, which is pure exploration. I'll sample from these arms. After some random amount of time, I'll say which arm is the best, with the probability of error control to delta. So k different arms of probability distributions are compared. Do not know the underlying distributions, but can generate samples from them. This is true in all the cases. Goal is only to identify the population with the largest mean and not to actually estimate the means. So that's the other thing in all these things. The goal is to find the best option, but not the value of the best option. That's where the computational advantage comes in. It's much easier to rank people. This guy is better, this guy is second, this guy is third, than to say this guy has level this. His ability is 86.54. That's a much harder thing to say. Then you are looking at central limit convergence rates, which are much smaller. I don't know, how many of you are familiar with central limit theorem? So you know that it has 1 upon square root of n convergence rate, right? That means to get a particular accuracy, the n needs to be massive. How many of you are familiar with large deviations theory? Chernov's theorem, Chernow bound Hovding inequality. So I'll mention that a little bit, but there you get exponential rates. So when you're comparing things, probability of going wrong typically has an exponential decay rate, so much faster. So you want to exploit these facts basically in your algorithms. Okay, so for random variables xj, j less than equal to a, goal is to find the j star, which is the design which has the maximum mean in minimum number of samples while controlling the probability of false selection to a specified delta. So you can imagine this, that I have 3 arms, 1, 2, 3. I'll generate these samples. I'll pull this arm, I'll get 1 red sample. I'll pull another arm, I'll get another red sample. In this case, I'll pull arms, I get these blue samples. These are the sample values. From these samples, I want to see which one has the largest mean as quickly as possible. When am I statistically comfortable saying that, okay, maybe this arm has the largest mean? Probability of making a wrong decision is less than delta. When am I comfortable doing that? All right. So I mentioned to some of you earlier that in case, because you've come in late or in any case the math has gotten too messy, you're not following it, feel free to do Facebook or whatever, just use your time well. So I will not be at all be offended. Okay, so some applications of pure exploration. So given stochastic models of different road network designs, so now it's a stochastic model. I'm not observing the road, I have a mathematical model of the road, finding the one with the least average congestion. This is the example which I just mentioned to you earlier. Given medicinal treatments for a given disease, finding the one that causes maximum benefit on average. before it is launched in the market. So you'll test it on some people and you want to find which one is the best one before this is the only one that you're going to use later. So you want to find out which one it is after, and you want to find out quickly. So this fits the pure explanation. One example which I'll do is setting hardness of questions in an interview. And I think I may have time to also do setting hardness of questions in an exam. So think of a GATE exam or a joint entrance exam. You have some objective, right? You want to filter out 10,000 people amongst 10 lakh people or something like that. So given that's the objective, what should the level of difficulty be in your questions? So I'll talk a little bit about that maybe if I get time. But that's what I try to do. I try to see problems which appeal to you just from real life. Okay, regret minimization. So let's come back to regret minimization. Let's look deeper into what kind of algorithms work well. So again, given k arms, each arm and pull gives a random reward. The reward at time t for each arm is given by x1t, x2t, xkt for each of these k arms. This is the mean mu I. Reward xit from each arm are IID. And for simplicity, I'll assume that these are bounded rewards, bounded between 0 and 1. That's just a normalization. But bounded makes things much, much easier. If these random variables were fat-tailed, if they could take extreme values with insignificant probabilities, then you have to worry about those things. So I won't worry about them. All right, at iteration t equal to 1, 2, 3, algorithm pulls an arm I of t and receives a reward, x of I of t, t. The learner does not observe the rewards from the other arms, right? That's what we discussed. This is my regret at step n. If I had pulled the best arm all the time, I would have gotten this reward. I pulled some other arm, I got this reward. And my aim of regret minimization is to sequentially pull arms so as to minimize the expected regret. So expectation of this, which is just n times mu star. Mu star is the expectation of output from the best arm minus E of xit. And you can see that I can compute things differently. If TIN denotes the number of times in the first n trials I picked arm n, every time I pick arm n, I incur a regret of delta I, which is mu star minus mu of I. Right? Mu star is the mean of the best arm, mu I is the mean of the ith arm. This is a regret I incur. This is deterministic now. So this times expected value of TIN, summed over I equal to 1 to k, is also my regret. That's just another way to do the counting. Right? Number of times you pulled arm I, and the regret you incurred every time you pulled an arm I, summed over all I. So this is the regret that I want to control, that I want to minimize. Any questions so far? Okay. So now I'll give you what works. So what I'll do is, my plan is in this thing is very simple. I'll mention to you two reasonable ways of doing explore and exploitation in this setting. I'll give you results for one, and the second one I'll prove for you. That's the only proof I'll do in this sequence of lectures, just to give you a flavor of what kind of mathematics is used, and in fact, to give you a flavor of the elegance of the mathematics that's used in this setting, how things are kind of kept very simple. So first is the epsilon greedy policy. So what I'm going to talk about is coming from this paper, Auer, Sessa, Bianchi, and Fisher 2002. At step t, sample each arm uniformly with probability epsilon t. You want to explore and exploit. So epsilon t you keep for exploration. I'll just sample any arm uniformly with equal probability, but the overall probability of that is kept at epsilon t. And with the probability 1 minus epsilon t, I'll use the best sample mean that I've seen so far. That's my best horse. Right? At time t, I have sampled all these arms up till now. I've seen what our rewards were from each of these arms. One guy was better than the others. So I want to exploit by sampling that, because that will minimize my regret. Right? Very likely that's the way I control my regret. But I'm also concerned that maybe at time t, I've not sampled everything. Maybe I've always been pulling the bad arm, and there is a good arm out there. So I want to explore as well. So with epsilon t, I'm going to explore. So now one can do intricate mathematics to see what's the right epsilon t that works. Turns out the epsilon t of this form does a very good job. So minimum of constant c chosen to be sufficiently large, I won't do the mathematics of this right now, upon t. The main thing is that the rate of decay is 1 upon t. And the idea is that if so this is 1 just because c by t may be greater than 1 to begin with. So in that case, you just explore in the beginning. Just explore everything with equal probability. But the idea is that, eventually as this algorithm goes on, whenever I'm exploring, I'm kind of suffering a regret. Because very likely I'll pick a non-optimal arm. Right? I'm giving equal weight to every arm. So that regret that I suffer should have probability 1 by t. So if I sum up my regret, it's going to look like log of n in n steps. Summation 1 by t up till n is roughly log of n. That you know, right? Summation 1 by t is going to infinity, but actually at a logarithmic rate. So that's a big point here, that you can actually show that for n large enough, all the suboptimal arms, this is the number of times I pulled arm I, which is not optimal, that's actually going to be log n times some constant d divided by delta squared. Delta is the minimum delta I. Delta I, remember, was mu star minus mu I. It's a regret every time I pull arm I. And the smallest regret is when the two arms are very close to each other. So delta is that. So this is actually the, really when I'm comparing these arms, the competition is between the best and the second best. And delta is the difference in the two means. So that comes in the denominator. But the bigger point here for you to appreciate is that in this game of minimizing regret, even this simple epsilon t policy which I showed you, if you do it roughly correctly, so you give, you decay with 1 by t rate, with constant c chosen well, the number of times you're pulling wrong arms is of log n type in n steps. So most of your effort is going on the best arm. At k minus 1 arms, you're spending log n order amount of effort, and the n minus k minus 1 times order log n is what you're spending your effort on best arm. So this epsilon t algorithm is very good in that sense that it's spending most of its effort on the best arm. So your regret, which is just going to be etin times delta I summation, it's going to be bounded by this, is also logarithmic in n. So this very simple policy made you a fairly, if you're not familiar with this literature, it's a fairly surprising and pleasing result that you can control your regret to order log n just by doing simple things. Yeah?
Intuitively, wouldn't one be led to think that once I do, or once I choose, or once I keep choosing my arms, and so for example, if n is sufficiently large, then one should actually start choosing a smaller and smaller epsilon t. For example, if I would have chosen epsilon t to be of order 1 by t squared,
right.
Then that log n would actually start to be, that log n will not appear, it will be finite then.
You're saying eventually, because early on if you keep your epsilon t is too small, you worry that you've kind of missed out on the best arm, you've not explored enough.
Okay.
Because the best guy just had some few bad samples, and you completely ignore it. So certainly, so that would not work. That would cause the regret to go up initially. But one could say, okay, maybe after long enough I can devise my algorithm so my epsilon t becomes smaller. That will have very marginal effect on the overall performance. Yeah. But 1 by t right now is optimized. So if it was more than 1 by t, if it was 1 by root t, then you're exploring too much. Then your regret goes up. And if it's less than that, you're missing out on the best guy, then also your regret goes up. Right, so logarithmic regret is the big message here. Now there's a paper by Lai and Robbins in 1985. These are statisticians who actually came up with, did a mathematical analysis of these techniques, and they came up with a proper lower bound. No matter which algorithm you use, this is the regret that has to be there. And then they actually came up with an algorithm which kind of matches it, very complicated. Since then, enormous effort has been built up to come up with algorithms which are simple and match the lower bound. And they have a following flavor. Now I'm going to give you an algorithm which is not quite the best one, but it's fairly close to it. But it's very kind of easy to absorb. So these are called upper confidence bound algorithms. So for an optimistic upper confidence bound on each arm, so form a optimistic so I don't know the mean of, the point is this. I could have sampled all the arms in the beginning, look at their sample means and just pick the arm with the best sample mean. Very greedy. But then you're not exploring, and you can you can fall into bad sample trap that, somebody which was really good had bad luck in the beginning, you just ignore it in the beginning. So that will increase your regret. So what you do instead is, rather than looking at sample mean, you come up with an optimistic estimate of the mean of the arm I, for every arm I. So this is called upper confidence bound. It's an optimistic estimate. This UCB is greater than the sample average, but converges to it as the number of samples increases. So you come up with some other number which is more than the sample average, but as that arm is sampled more and more, it converges to the sample average. It has a, more comfortable you get with sample average, that's what it converges to. And this number is going to increase if the arm is not sampled for a long time. So if I don't sample an arm for a long enough time, then this estimate that I have keeps on increasing. And what I'll do, once I have these kind of UCBs on every arm, the algorithm simply involves sampling the arm with the largest UCB. So essentially what's going on is as follows. I'll make this thing more precise as you go ahead. For each arm, you'll have an index. And at every time, what you do is you pick an arm with the largest value of the index. And the index has this property that it's not quite the sample average, but it becomes closer to sample average as the number of times the arm is pulled becomes large. If an arm is not pulled for a long time, then this index increases. Kind of tells you it's time to explore a little bit. And the exact form is as follows. So sample each arm once in the beginning. At step T, select an arm with the index I of T. So how do I choose which arm to select next? Choose an arm with the largest value of this index. So what is this here? This is saying sample average of arm I. This is the number of times arm I has already been pulled in the past T-1 trials. So this is the best sample average that you have at time T for arm I. Is this clear to everyone here? The notation should not confuse you. I've reached time T, I've reached the 52nd step. In 51 steps, I had sampled this arm maybe 11 times, so I have the average of that with me. But I won't just trust the average. I'll modify this average by this index, which is actually square root of 2 log T, these are well-chosen numbers, divided by the number of times this arm has been sampled already, 11 maybe, and square root of this. So this is the index for arm I. Amongst all the arms I, I'll choose the one with the largest value of the index. So it's kind of getting the right flavor that I want to basically choose the arm with the largest mean. And you expect this to kind of, as I sample lots of arms, lots of times, you expect this to be very close to the true value of the mean. So, by and large, you'll pick the right arm. This guy here, if some arm is not sampled enough, if this particular arm I has a very small number here, say number 5 where everybody else has number 20 or 30, then, because this denominator is small, this index will be larger. So this arm will want to be sampled. And if I don't sample this for a long time, this numerator here will keep on increasing, log of T. So again, that index is increasing. So it's kind of telling you how to explore and exploit in a very kind of optimal manner. But do you see the flavor of it? It's very simple and elegant. You don't need to do detailed analysis. Just maintain these values for each arm and keep track of how many samples you've generated, and choose an index which has a larger value. That's the arm you sample next. So UCB does a good trade-off between explore and exploit. That's what you want to do. You want to exploit guys which are showing you large mean, but you also want to explore guys where this is small, where the number of samples is small, and we've not explored for a while. So each suboptimal arm is going to be sampled order log n amount of time at n number of steps. Also, what's nice is that they are working, this log n property for n steps is not just true asymptotically, it's true for every n. In some sense, you don't want to live in the world of asymptotics always, right? You want to have something which works always. The expected regress is of order log n in n steps, and this can be shown to be much better than epsilon greedy. In some sense, epsilon greedy messes up because when it explores all the arms. It becomes indifferent to the fact that you knew some arms were much better than the other. Well, this is much, much more refined. All right, so before I show you the proof of this, I'll show you the flavor of how one proves such things. Hovding's inequality. So many of you said you're not familiar with Hovding's inequality. But you're familiar with central limit theorem and all of that, right? And law of large numbers. So think of Sn as sum of independent identically distributed random variables y1 through yn. And again, for simplicity, I'm going to assume these random variables are bounded between 0 and 1. Right? And their mean is E of yi. So law of large numbers tells you that Sn upon n converges to the mean almost surely as n goes to infinity. right? Central limit theorem tells you that the difference of these two, Sn by n minus mu, when you multiply by square root of n, that becomes a non-trivial quantity, Gaussian distribution, which tells you that the difference is going to 0 at the rate 1 upon square root of n. So rate of convergence. But now this is saying that the large deviations, deviation of mu plus a for any a which is positive. So now this is saying that the sum is taking a large deviation. This average is moving away from mu plus a, from mu by an amount a. So this is a much larger deviation than what central limit theorem allows you to look for. Central limit theorem only looks in the region of 1 by root n away from the mean. This is going to decay at an exponential rate. See, this n is here. So this probability is decaying very fast. The probability of seeing these large deviations is going to be very small. What's nice about these bounds is that I haven't told you anything about the distributions of yi's. I've just told you that they lie between 0 and 1, that's all. So it's very robust in some sense. It's true for all yi's lying between 0 and 1. If you wanted more distribution-specific bounds here, then you look at what's called large deviations theory. The large deviation theory is pretty much, the basic thing, the basic content is look at these averages and look at these kind of probabilities and understand how these probabilities behave for large n. But this is a robust kind of an estimation. It's true for all yi's which are between 0 and 1. And this is a deviation on the other side, same thing. So is this clear? That as a becomes larger, this is increasing as a square. Otherwise, as a function of n, it's decaying exponentially. Those are big things you want to keep with you if you've not seen these things before. That indeed large deviations have a very tiny probability. But these are bounded variables. What I'm saying would have also been true for Gaussian variables. Gaussian you understand, right? Normally distributed. What's nice about normal distribution also is that the tails are very small. A normal random variable taking an extremely large value, it's a very tiny probability. Decays, being greater than x, roughly decays as e to the power minus x square. This is to differentiate from fat tail variable where probability of random variable being greater than x has 1 upon x square probability, let's say. It's important to understand these things because a lot of the catastrophes are caused by fat tail variables. A lot of the probabilistic, a lot of the randomness that can be controlled and managed is when it's light tailed. Then you can kind of approximate structures deterministically. So right now I'm in the light tail regime here. These are, okay, so now how do we prove that the regret is going to be of order log n? So I'll show you the analysis for it. It's very cute. I don't know how much I'll be able to communicate it clearly. Let CTS be 2 log t upon s. Remember, let's just go back to the algorithm. 2 log t upon, so s corresponds to the number of times that the arm has been pulled. So I'm just calling this thing as CT and then TIT minus 1. Right? Square root of 2 log t upon s. TIN is the number of time in n trials that arm I has been pulled. So our algorithms give it at least one try to begin with. In the first k trials, every arm gets pulled once. And then from k plus 1 to n, this is just the indicator function that at the trial t, arm I was pulled. Right? I can, what I'll do is I'll segregate this, I'll separate them as m plus, again, this indicator function. And now I'm assuming that the arm I has been pulled at least m times. So basically, I've taken this indicator function here and cut into 2 parts. Either the total number of times the arm I is pulled is less than or equal to m, or it's greater than or equal to m. The less than or equal to m part gives me this term here. When I sum up the indicators, it's bounded by this m. And now I'm left with this. So this joint thing has to happen. That at the tth trial, ith arm should be pulled, and at that time, already I should have pulled the ith arm m times. This is a clever technique because what I'm going to do is, the algorithm has this flavor that I know that there's a right m, after which you stop kind of pulling this arm that much. After that, the probability of pulling this arm becomes very small. So I'll just plug in that m here. And all these terms I'll show have very small probability. So most of the expected value of this is going to come from this m that I choose. So that's, you don't have to pay attention to this, but it's kind of cute to see this. It'll help you read these kinds of papers. So now you say to yourself, okay, when will I pick up arm I? Arm I here, by the way, is a non-optimal arm. at this trial, well, what has to happen? This arm has to win against the best arm. Right? That's how I'm deciding the index. So the ith arm's index at time t is going to be just the sample average of this arm plus the C term, this optimistic term that I have, C of t minus 1, ti t minus 1 from here, just by definition of the algorithm. So this has to defeat the best arm, x star t minus 1 plus ct minus 1, t star t minus 1. And the thinking is for m appropriately chosen, thereafter these things happen with very small probability. You stop winning with the best arm. You just have to choose this m carefully, right? And now a proper, the problem with doing mathematical analysis of these things is, if you ever look at these papers, that this term here, t star t minus 1, is number of times best arm has been pulled in t minus 1 trials. This term ti t minus 1 is the number of times ith arm has been pulled in t minus 1 trials. These are random quantities. It's very difficult to do analysis with random stopping times, etc. What you do instead is, because you know in your hearts of hearts that I've chosen m in such a way that these things in any case happen very rarely, you bound them. So this I'm going to bound by minimum of x star s. Minimum, maximum I can deal with much more easily. So minimum of x star s, this is the best arm sample average, all the way up till time t. And maximum of x star, this is x hat is, this is the sample average of the ith arm from m to t. So I can upper bound this event by these events. Basically, the intuition is that after m well chosen, even the minimum sample average here plus this term is going to be typically going to defeat the maximum of the sample average plus this term. So this probability of seeing this event happen is going to be very small. That's what's going on in the back of my mind when I do this analysis. And because I have minimum and maximum here on the indicator functions, I can upper bound them further, by applying union bounds. So I can just look at these events separately as, for each s, x hat star s, this is the sample average of the best arm after s steps, plus CTS is less than or equal to x hat ISI plus CTSI. This is the sample average of the ith arm after SI steps. Right. SI can take values from m to t minus 1. S can take values from 1 to t minus 1. So this is just kind of upper bounding this indicator here by these things. And I'm summing over all possible values of S and all possible values of SI. So it's a proper upper bound. But the intuition remains that all these events will have small probability. Okay, now, if you're following so far, if you're not following, that's fine. I'll just show you one more slide, then we'll move on. But I want to control these things to say that I can control the number of times arm n is pulled. So big picture again, I expect arm I to be pulled about m times because I have inbuilt in my algorithm some exploration. Beyond that, I don't expect it to be pulled. So I just kind of isolate the events when it will be pulled even beyond m, and now I'll show that the probability of these things is going to be small. Okay, so observe that the best arm loses to the ith arm when this happens, and this implies that at least one of the three must be true. Either the best arm saw large deviations. It was much smaller than its mean. So this is average of the best arm and it's been pulled s times. It's less than or equal to mu star minus CTS. So either it saw unusually small value, these S samples gave me a sample average, which was unusually small, or the ith arm saw an unusually large value, mu I plus CTSI. CTSIs are just chosen so that this event has a small probability. If those things did not happen, if these two rare events did not happen, that means your x star s is greater than or equal to mu star minus CTS, and x hat ISI is less than or equal to mu I plus CTSI. On that space, then it must be that the CTSI is less than or equal to mu star minus mu I, meaning, so this must be true, or this must be true, or this must be true. So if these two are not true, then this must be true. Or if these two are, so more importantly, if these two are true, then this must be, if these two are false, then this must be true. That's what I want to say. One of them has to be true. So all I'm saying here is that you have to observe that if this is false and this is false, then you can easily conclude, and maybe not in real time, that this must be true. Right? So this is true is a small probability event. This is true is a small probability event. Both of these are false. That means the non-small probability event happens. Then this must be true. So anyway, so that kind of helps you get a control of these things, because for this to be true, your CTSI must be bigger than mu star minus mu I upon 2. And CTSI is kind of a decreasing quantity. So you couldn't have, you couldn't have sampled the arm too many times for this thing to be true. So let's just see. So what I'm going to say is that, for this to be false, no, hold on. For this to be true, so I've taken the wrong rare event, I can use Hovding's inequality. There should be equality here. This should be less than or equal to here. And upper bound this probability by t to the power minus 4. So there's a typo here. But the point I'm just trying to make right now, I'm going to lose you on this, is that this event is basically that the sample average takes an unusually small value. And this is the probability of sample average taking unusually small value. Now I can apply my Hovding's inequality, which I showed you, to get a bound on this probability. And that bound just turns out to be 1 upon t to the power 4. That's just a calculation. Similarly, for this to happen, it's a rare event that's going on. This sample average took an unusually large value. I can apply again my Hovding's inequality and show that this will also have this probability here, 1 upon t to the power minus 4.
Bound, so there must be an equality.
There's an inequality here. This should be less than or equal to here. Yeah, and these two are equal. There's this typo here. Okay. And the third cannot happen if I choose my m to be. So, if both of these are false, then this must be true. But this cannot be true for m greater than or equal to 8 upon log n by delta I square. So this is saying that, okay, your CTSI should be big enough. CTSI is shrinking with s. It cannot be that big. In n steps, you can, t must be less than or equal to n. And SI cannot be that big because, CTSI has to be bigger than mu star minus mu I upon 2. So if SI is bigger than this number here, then this cannot happen. So these many samples, you just give it to the ith arm. These many samples it will do. And thereafter, everything, this cannot happen. So one of these things must be true, and these things have small probabilities. So that's kind of the logic. So, because I've got t to the power minus 4 here, if I go back to my summations here, if I can show the probability of this is less than 1 upon t to the power minus 4, even if I sum it so many times, I get something which is just going to be a constant. So, and this m was chosen to be 8 log n upon delta I square. So that gives me a bound on expected number of times ith arm is pulled in n steps to be 8 log n upon delta I square plus some positive number, which is not increasing with n, which is independent of n. So that gives you a clear bound that the number of times ith arm is pulled is increasing at most logarithmically in n. Yeah?
So in the previous slide where we applied Hovding's bound,
Yeah.
that means we are assuming some distributional assumption on these x's.
So
Hovding bound, we've either applied for bounded random variables.
0, 1.
Okay.
Yeah, so that's the point I had made here, that all these variables are taking values in 0, 1.
So that means these x.
Right, right.
We have an assumption.
So everything I've said right now is for bounded random variables. In fact, that's been the kind of trait of this community, that they typically consider bounded random variables. And then they generalize this to sub-Gaussian random variables with Gaussian tails. So these are easy problems. But there's been sufficient work on kind of extending these to more general distributions. So all of what I'm saying right now, in fact, my student is working on this, extends to xi's having a known bound on a moment. So maybe the third moment of xi is bounded by some constant that you know. With those known bounds, you can replicate most of this.
Yeah, because there are other kinds of exponential bounds for like general random variables where you have constraints on moments and so on.
Sure. So you can use Bernstein's inequality. Yeah. So people do that. For a Gaussian distribution where mean and variance both are not known. Bernstein inequality turns out to be quite useful. So I'm keeping things very simple right now. Yeah?
This inequality is tightest.
No, it's not the tightest. It's not the tightest. It's not the tightest.
And the second inequality in the previous one.
This one here?
The previous.
Hovering, you mean?
The second inequality is this tightest.
These are pretty tight. This M has to be chosen carefully, but these probabilities are just going to show up in the extra constant term, not in what multiplies log n. So if it's not multiplying log n, whether I put 5 or 20, it doesn't really matter. So in that sense, you don't need to be tight there. You need to be tight on the constant with next to log n. That you want to get correctly. So that way, by getting 8 here, we're not doing a great job. But it's just very easy to see why it's log n, so that's why it's nice. So let me just talk about this a little bit. So many variants and generalizations exist. So as I mentioned, there are adversarial bandits where now when I pull an arm, the output is not a sample from a probability distribution, but nature gives me something bad, something bounded between 0 and 1, but worst case thing. What do I do in that case? So there's elegant theory to how to deal with adversarial bandits. Continuous arms. I assume that I had k arms right now, but I could have uncountably many arms, but the rewards are somehow continuous with the index. It's like solving a stochastic optimization problem in a continuous space. See, this is like, from discrete number of arms, I'm trying to figure out which one is the best and focus on that. But now you can imagine from a continuum of arms, you're trying to figure out which one is the best and focus on that. So a lot of work has been done on these things. General arm distributions, exactly your point. That beyond bounded variables, you can have more general distributions. Then maybe you can use other concentration inequalities. So hovering inequality is an example of concentration inequality, which is essentially telling you that Sn by n, average of IID variables, concentrate around its mean. Probability outside the small region around the mean is very small. The mass is concentrating. So there are more general concentration inequalities, which are the essence of this kind of analysis. Lower bounds on regret are known. So this is by Lai and Robbins' paper in '85. So you can actually prove that no matter which algorithm you use, expected regret has to be log n is the term here, and this is Kullback-Leibler distance between Fi and F star. So if you don't know what Kullback-Leibler distance is, I'll come back to it in my next few slides. So but nonetheless, the point is this is known, and now there are KL UCB algorithms, Kullback-Leibler UCB algorithms, so exactly your point, that actually match this for large n. So these have also been developed, but this lasts just 4 or 5 years, this work here. It's quite elegant because they need to come up with very elegant concentration inequalities to make everything work. So that's new. That was not there earlier. And again, these index policies are very simple, very easy to implement. Okay, so this is what I was going to talk about for regret right now. Now I'll move on to pure exploration. And there I'll talk more about some of the work that I've been involved in lately.